So, hello everyone. My name is Jan. I'm a co-founder and technical lead at Zircuit, and I'm proud to be talking to you about how we migrated from a zkEVM, so an Ethereum virtual machine, to a zero-knowledge virtual machine without the E. I think I said that right. So we don't want specialized circuits, and I'm going to talk about this. Now, I promised in my talk that it would be friendly to people who don't know what's going on and to technical people near the end. I'm going to try to stay true to that mission in the 30 minutes that I have. I see that's actually 25 minutes, so this might be a little fast, but let's get into it and see what happens. So first, the background. What's a zero-knowledge proof? If you don't know, I don't want this topic to be relegated only to side rooms and people not talking about it on the main stage, so I thought I'd reintroduce it very quickly. A zero-knowledge proof system is a way that a prover, someone proving that they have some knowledge, can convince someone, a verifier, that they have that knowledge without revealing any of that knowledge. And this is some nice fancy math that's been around for a while, but it's seen recent adoption in part due to Web3, large part. And if you don't understand what the prover or verifier is actually trying to do, it's generating some math to convince someone, doesn't matter. The real takeaway is at this bottom of the slide, which is I know a valid input to a computation and the output, and I can prove to you that I definitely computed it correctly. So I executed the thing that I want to do correctly. And why do we care about this? Well, we'll use it for zero-knowledge proofs. And we're also going to be talking about snark. Sorry, I have to introduce this very, very quickly. If you do hear me talking about a zk snark is just a zero-knowledge argument of let me slow down and go to the slides. So a zk snark is just a proof system by which it's zero knowledge. So the person proving actually doesn't share any knowledge, doesn't leak the secret that they were supposed to have. It's succinct, and this is very important. The proof is small. It's not interactive in the sense that the prover can give the proof to someone and then walk away. They can leave the stage. They can stop talking to a blockchain. They can just leave. There's other definitions, I'm sure, that they know something, that they have an argument of knowledge, that they know something. And what we're really going to care about here is succinct and non-interactive, right? So we want a small proof. It's always been sort of very important to get scaling to work on Ethereum, and non-interactive so that we can generate a proof and not have to sort of argue with the person back and forth that we do know something. And in fact, most of the time, we won't care about the zero knowledge. We won't actually keep anything private. Zircuit does not keep anything private. And through all this math, to get the succinctness and non-interactive properties that we want, as well as the others that we don't care about as much, perhaps, we have to do some stuff. And this usually introduces an overhead. A lot of the first problems we have is that you need to redefine your computation or the thing you're trying to prove in a very specific domain-specific language. So you suddenly have a huge bottleneck for developers to actually go and build out a system to do the thing that they want to do, to prove to other people that they know some knowledge. They have to be very specialized. They need to learn, some part of the math, maybe not all of it, maybe some of it's in a math paper, some of it is a little bit easier to understand, but they have to do something very extra. The upside is the tooling around this has gotten better over the years, and at least they don't have to do all of it by themselves. There's, tooling that will give you the verifier code, for example, to do this as well, often in Solidity, which is very nice. Even if they do all that, though, you're probably going to need different hardware to run it, or at least it might not be the hardware that you expect. The requirements have gone down since a slide like this first appeared on one of my decks, but there's generally a barrier to getting these things to run in a very short period of time. And so you have hardware requirements going up or costs going up, and this is also a problem. And we can't necessarily solve both of these problems, but we can certainly talk about solving the first one by using a general purpose zero-knowledge virtual machine. And that's what we're going to do. And to convince you that this is a worthwhile example, this is a sample, I think, from the Fibonacci circuit in Halo 2, which is the proof system that, up until last week, Zircuit was using to prove execution of Ethereum blocks. And I don't really know what it's doing here. It's setting up some columns. There's a whole bunch. It's so big that I can't fit it on the slide. I don't think that's a surprise. A lot of code can't fit on slides, but there's a lot of verbosity in these domain-specific languages, and there's sort of a way to think about your programs in these languages that becomes problematic. You need to start thinking about things as chips or circuits. You need to get them to sort of compile and be configured in nice ways. And that's not something that the average programmer might know how to do very easily. And then you have to define all these things so the constraints value to 0, and you're doing this all over finite fields rather than the integers. And maybe you don't even know Rust. That's a whole other story. We can't really fix that one. But it's a very difficult process. And it's very, very difficult if you're developing a complex system like a rollup or an Ethereum client. And so getting away from something that is this verbose into something that's simpler is going to benefit everyone. And if you do have to go down this route, what you do, and I'm showing this here because I'm going to change this image as we go through the talk. You have a program that you need to rewrite, generally just once, into this domain-specific language version of it. It'll generate a verifier for you. Typically, you only need to do that once. And then you feed it inputs. You execute the DSL version of the program as much as you want. Every time you do that, you get a proof that you can verify. So this is fairly straightforward, but a lot of those arrows are hard to do. Right? In particular, the rewrite stage is very, very annoying for most people. And then if you do that, the computation lift goes up, as I said. It can be as high as 10,000x. This is old news, I think, but I still want to say it so that people know why we care about trying to optimize these things. The complexity is very difficult, and how do you be sure that you actually wrote it correctly? Because if it's that verbose, there's probably room for errors, there's probably bugs. And then it depends on the prover that you're using, and there's a whole bunch of things. You may also have to do other cryptographic things to get your system to work, like a trusted setup, where you go talk to people and get them to contribute randomness and hope that they throw it away. And you should do it yourself, all of that. So there's a lot of challenges to getting zk off the ground. And it'd be really nice if we didn't have to do all of this in isolation. Why do I specifically care about this? Because I'm trying to build a zero-knowledge rollup. And while Zircuit has been existing on mainnet for a year, we also saw that all of that maintenance to maintain that zero-knowledge system was really painful. It was kind of an annoyance. So we're a rollup, so we're a layer 2, we're a blockchain. We produce blocks that we get from transactions, which either are deposits or from other people using our network directly. We built some blocks, and then we try to prove that we did not cheat, right? That block was created in accordance with the execution engine we're using, which we would really like to be the same as Ethereum, because we're trying to make Ethereum go faster. And so the picture sort of looks like this. You get some transactions, you build some blocks, you prove it, and then you verify it. It's a little bit misleading because there's probably supposed to be an arrow from the batches back to the prover so that the provers actually read from the layer 1 and prove the right blocks, not just some blocks. But then a smart contract says, OK, the proof is done, and now the layer 2 sort of has all the nice properties you want. In general, when anyone does this, we don't usually care about zero knowledge. There are some privacy chains out there that are doing great work, and they do care about that zero knowledge. We do not, so I will ignore that for the rest of the talk. But the main challenge with this approach is getting the Geth or Ethereum client, whatever you're using, to actually be the thing proved. So that's rather difficult, but it's not just that. You also need to make sure that deposit transactions are read. So the state transition function of you building a new rollup actually is more than just Geth. It's making sure that you didn't ignore deposits so that people are using your chain in the entirely correct, complete way. But if you get all that, once you verify a proof on chain within a single transaction, you don't need to wait days, right? You can get it right away. So this is where we use zero knowledge in rollups. And if we go back to the picture, it sort of looks like this. So I take this EVM. This is oversimplified and not technically correct, but it gets the idea. I had to rewrite that into a zkEVM. So I had to do all that big verbose zero-knowledge proof rewriting for a very complicated piece of software, namely one that operates Ethereum. And then every time I get some blocks, maybe I'll call that a batch of blocks, maybe it'll be a single block, maybe it's a transaction, depends how you want to prove things. I shove it into my zkEVM, and I get a proof, and I verify it, and things go very, very well. And so that doesn't sound so bad, and if I've done all this work, why do I care about switching now? Right? It seemed like it was a real pain to build out the code, so why do I care? Well, some parts of me don't care. I think it's actually really nice. I have complete control over my circuits. I can optimize them, right? I can do very, very cool things with GPUs and custom gate evaluations in Halo 2 in order to really get the maximum performance out of these systems. I think that's something that's very exciting, and we have cryptographers on staff who are really excited to do that type of work. It's work that I don't necessarily understand anymore, but it's stuff that really pushes the limits of what both the hardware and the software is capable of doing. So that's really nice. But unfortunately, the downsides are really, really bad. The upside, get you a little bit more performance. The downside is you need a lot more staff. And that's really, really problematic. Because when you start to go to change these circuits, there's always a need to make sure you didn't break soundness, or that they're still optimized, or that they're still doing what you want. And you have to sort of change things all over again. And then if you do all that, as I mentioned, there's no way or very few ways to detect bugs or to check correctness. Formal verification is catching up, but it's still slow, especially when people were using different proof systems. Maybe your proof system didn't have the right tooling, but you were already sort of locked in or you didn't want to change. Nonetheless, there's challenges. And then, how do you actually optimize it? it can be done, but it is challenging. And then if you care about privacy, you got to make sure you didn't accidentally leak some knowledge, right? So on a rollup, that wasn't too concerning for us, but it is a concern in general. And it's a real concern. Over the last so many years in the space, right, the execution engine of Ethereum has updated. It will continue to update. Fusaka will hopefully come sometime later this year, maybe by DevConnect in Argentina. But the last one that we were really annoyed with was Prague? Yeah, one of these. Cancun introduced opcodes. When we went live, we didn't have support for those opcodes, so we had to change it. And then Prague went live, we didn't have support right away. We were like a week behind it. But the amount of effort to get the engineers to support these opcodes was through the roof. Like several of them for several weeks or several months, depending on the specific allocations. And to allocate that many resources just to say that we're EVM equivalent or EVM compatible, which is perhaps more accurate and a little bit weaker, is really annoying from a leadership point of view. And it's not good for the community because we've all been asking for these releases to come more quickly so we get cool new stuff on Ethereum. And if everyone has to do that type of resource spending to be just at par with Ethereum, no one's going to be able to beat Ethereum. And I do think there's a lot of interest in getting rollups to do more than just EVM. I don't know what those things are, but I think that would be really cool. But most teams are very scared of not saying they're EVM equivalent or not being compatible with the EVM. So this is going to continue to happen. We needed to figure out a way to do this. And when we started to see that lift, we thought maybe we shouldn't be building out our custom circuits. And thankfully, everyone else was on the same page with us. In fact, they probably had the idea first. I'm not trying to claim we were first with this idea. We didn't build the zkVMs I'm going to talk to you about later today. So of course, we didn't have the idea first. But what if we didn't need to have the specific thing we were trying to prove be rewritten in a DSL, but we could take a virtual machine that can compute anything and put that in the DSL? What if we could just do that once? Then we could feed as input Ethereum clients. And this is the story you probably heard, but I'll say it again here just for completeness. If we could do that, that would be really, really good, because now I can take my inputs and make them Ethereum, and then that I can change whenever I want with Ethereum, because if Ethereum is going to do a hard fork, clearly they have the code to do that, and then we're good. And in this case, we can target a language that everyone knows, or at least more people know, or at least is easy to prove. One of these could be RISC-V or RISC-V. And then the inputs to that VM can just be in Rust. So I said we can't fix the Rust issue. Oh well, at least Rust is more popular than Halo 2 specifically. And now the developers just need to write the input to that, and they don't need to understand the DSL, which is really, really cool. So they don't need to worry about finite fields or having an inverse to an element or anything like this. Great. And now they exist. Over the last several years, they've become really, really popular. A couple that I have been following more closely than others are RISC-0, I don't know why it's so pixelated, SP1, Jolt, Hermes. There's a bunch out there, and they're becoming really, really performant. And so now, if they're open source, and thankfully a lot of them are, we can actually use them and use them to replace our own zkEVM. And if we could do that, the system will look something like this. You take your ISA, your virtual machine that you no longer sort of need to maintain as a rollup developer. You just assume that there's a nice instruction set architecture. You write that in a zero-knowledge domain area. So over here, you have a zk virtual machine, and then you put as input whatever you want. And we'll see later that I'm going to put in my state transition function for a rollup in there. And now we're really good because I can change the inputs as much as I want without changing more or less the rest of the bottom of the picture. And in particular, if I have a rollup, it might look something like this. This is oversimplified. We're going to put the EVM from down here up into the inputs of the program, and suddenly we're in good shape. The L2 blocks there is a little bit inaccurate. There needs to be L1s to derive where data went and things like this, but more or less, this is what it looks like. You give me the EVM and the thing that was supposed to compute, and I can convince you that it computed that thing correctly. Because of all of this, my life gets a lot easier. A lot of other people's lives may not get quite so easy, but they're interested in this. But we can share the load, right? We can now have a community effort to make sure that the zkVMs that we're using are correct, have been set up correctly, and are optimized. If I am using a zkVM that other rollups are using, we're all incentivized to make this really good and fast, because we can share the results and get it all done together, rather than just me having direct ownership over my circuits where I might break something. I don't want that, but it might. You can also standardize and compare results a lot quicker. When the first time we came out with optimizations to our Halo 2 system, it was very difficult to convince other people that we did something, because if the other Halo 2 circuits were a little bit different, people would ask questions and not see an improvement, even if they were there. This time we can be very standardized, right? We can say, okay, if you can prove this specific Ethereum block faster, that's it, you're faster. It's a lot easier this way. And now, the greatest part for me, and probably a lot of people, is that the developers who want to prove something no longer need to know this thing. The downside is customization might be harder. A lot of the zkVMs have open source software for the VM, but not necessarily the provers. So the provers might be a little bit slow unless you pay them. Or maybe there's a way you can make it faster yourself, but it isn't an issue. And then, it might have problems with other applications of zk. If you're trying to do something on a phone, maybe the VM is still a little bit too powerful. You can't do that. And you got to rewrite something from scratch. Nonetheless, probably not an issue for a rollup. The next one, though, is how do we actually use it? I built all this framework to get migration, or to get Halo 2 working on a rollup. How do I actually go over to a zkVM? Thankfully for us, it wasn't too hard, and I'll try to tell you exactly why that was. I only have 10 minutes left, so it's going to be kind of fast. We had two questions. We said, first, how do we actually do this? We made a lot of changes in Zircuit's specific architecture to make sure that the Halo 2 provers we decided to use would actually be reasonably competitive. I don't think we ever won the race for fastest block time as much as we wanted to. I don't think we ever got close. I think we got close, maybe, but we didn't win. We made some changes, and then how do we fix that? And then second, which zkVM? Because I showed you a slide with at least 4 GitHubs, there's probably another 4 that are very close to that, and then there's probably another 4 that are more obscure, but also still very performant. And I bet there'll be another 4 by the end of the year. So what do we do? To answer the first one, we can say, oh, we actually had good planning. There's 2 main issues here. One is, for a lot of the Halo 2 circuits, what we had talked about in the past was changing out the Kesek-based state trie for Poseidon. This allowed us to prove blocks in the Halo 2 proof system a lot quicker than if we didn't do that. But it would have made a lot of changes in a lot of other places. And we saw it was so damaging, and we thought that this would actually be effective as a strategy, the zkVM strategy, that we actually just added it. So we actually had dual state roots being pushed out, and I gave a talk about this in Denver, so that was pretty good. And we also thought we should have modular prover architecture so I don't have vendor lock-in with anyone. So I can prove my Halo 2 proofs on a different proof system, whether that's Halo 2 or something else, on different hardware, on different clouds, on things like this. Luckily, both of those are very valuable. They're both able to help us right now. So now that I have dual state roots, I can actually disable the one now that's zk friendly for Halo 2 and go back to my Kesek one. Makes me very much closer to Ethereum, which I'm very happy about. And this modular design also means I don't have vendor lock-in, and I'll talk a little bit more about that. So that's specific stuff. Generally, if you're just forking the OP stack, all of that goes away. You don't need to worry about that, except maybe building out the prover pipeline. That modularity is something we probably want to build out, if you're going to do this. And we are seriously going to consider open sourcing that, but we still have other things we need to open source before we get to the modular part. But talk to me if you have questions. So the more interesting question then is which zkVM, and this is what we found. We found that the best way to do it was actually to optimize for time to market, not necessarily best performance. Now, that's not to say we're going to pick a very slow prover. The goal was not to pick one that proved in hours. But if something proved in 5 minutes or 5 minutes and 15 seconds, I didn't care. It was a little bit different. When you get to real-time proving on Ethereum, this will matter a lot. You need everything to come under 12 seconds. For a rollup, which has a delay period of not 12 seconds, I am less concerned about this. And so what we did was we found Kona, SP1, some partners, and we put our own code into this. And so I'm going to talk to you a little bit about what we changed and how we did that and why we did that, keeping in mind that we optimized for go-to-market time. So first, these 3 things or 4 things are critical, and you may have seen them before. A lot of them make up what would normally be called OP succinct if we didn't make modifications, but we did make modifications, so I won't call it OP succinct. But OP succinct is typically Kona, SP1, the prover, and a prover network, namely the succinct prover network. And we took all of these things and we modified them to make them work for us. Kona is the state transition function for optimism-based rollups, and we were optimism-based. We forked their code. We started building on that. We tried to make circuits work there. SP1 is a state-of-the-art Rust zkVM, which will prove any inputs in Rust if you can get it to compile and all that, the usual conditions. And then a prover network. We do want to do some stuff in-house, but it was easier to also talk to some people, and then the changes. So let me get into it. So as I said, Optimism built out Kona as a way to measure or to record or prove the state transition of the OP stack chains. So not only building blocks correctly, that the EVM didn't do a bad addition or something like this, but also that deposits in L1 blocks were correctly read and included in the chain, that the OP node is actually proposing those deposits inside the L2 blocks, and that the L2 block is being built correctly. And so it was designed as a fault-proof system so that they could prove whenever there's a challenge very quickly who is wrong on Optimism. We are a zero-knowledge rollup. We're aiming to be a zero-knowledge rollup. So we wanted to prove every single block. So this part needed to change a little bit. And we'll talk about that in a couple of slides. Nonetheless, we're standing on the shoulders of giants. OP Succinct came packaged with SP1. We found that this was more performant in our own experiments than other alternatives. And it also has a nice set of other options that we can change. So if we want to go potentially quantum resistant, maybe we can use the built-in Stark some way. I think the proof size might be too big to do that out of the box, but you get a whole bunch of really cool stuff out of using SP1. Their use of precompiles is very important, very performant, and we got it to work. And then we went with partners, and the biggest question I'll probably get is why didn't we use Succinct? And that's mostly because Sindri gave us optionality for different zkVMs. Although we trust the SP1 prover, if we want to change because we suddenly care about having the absolute most performant one, or because there's a bug somewhere, or for whatever reason, we wanted to go with a third party that would actually allow us to have that flexibility with great ease. And they provide a nice zkVM API infrastructure, so we just send them the things we want to prove. They come back with a proof, we're happy. And so what did we have to change? Well, we had to change a lot of things. First, Kona was built for fraud proofs. We wanted to be validity proof, so we had to make sure it proved every single block rather than just when things were challenged. Other code bases started down this route, like Kailua. We found it was easier and more performant to modify Kona in the ways we cared about. Zircuit also has its own specific functionality. We had to change that and put that into the state transition function. So if you get a quarantine transaction, you need to deal with that. OP Succinct also out of the box talks to the prover network at Succinct, not Sindri. So we had to change that. That also means we have great modularity and we can switch back and forth whenever we want. And then there's other changes that we're about to release, which we haven't, which is including stuff to derive DA in a more optimal fashion. So reducing the amount of things we have to prove, number of cycles. So we picked SP1, and that actually went live last Monday. Yeah, it's been live for 2 weeks now. So Zircuit's actually now proving every block. We're using SP1. It's very great times. And if we look back at the picture, what did it end up looking like? Something like this. We have the SP1 zkVM. We have our EVM and Kona, which will then read data from the L1 block. So the batches from the sequencer will go into there. The deposit transactions obviously go into there. Anything else is there. We prove that that is executed correctly. We verify that on chain, and now we have a proof that we are a zk rollup. For the actual migration, there was a lot of practice, and I'm running out of time, so I don't have a lot of time to say too much about it. But essentially, we picked a hard fork time sometime last Monday. We set up a new sequencer to take over as soon as that block hit, and then we deprecated the old one at the same time. So going forward from that block forward, every L2 block has a SP1 proof attached to it. We're proving every single block. We did wait for the old prover pipeline to finish because we had some stuff pending. We wanted to prove what was left. And then we just proceeded. So that was sort of it. I'm going very, very fast. On the technical side, I won't go through too much of it, but there was a lot of changes. A lot of our code base from Optimism had to change. The one that I think is most important is first, we disabled our zk-try, no longer need it. And second, we no longer have this notion of a circuit capacity checker. So us and Scroll and some others, when we were using Halo 2-based provers, couldn't prove every transaction. Sometimes precompiles would have too many calls to them, and our provers just couldn't handle it. And so suddenly that's gone. And now we're really, really happy about that. We also added a new precompile P256 verify, and then we upgraded a whole bunch of things from Optimism because they had also been chugging along and doing development. We changed the proposer. I'm running out of time, so I'm not going to talk about the smart contract changes. A lot of stuff changed. As a takeaway, I want to talk a little bit about the performance, and these numbers are not 100% accurate, but they're a really good indication of why we're also excited to do this, even if developer time wasn't my main concern. And that is about a 10x speed up if we have GPUs. These numbers are not necessarily the best we could do, but with the Halo 2 prover, we were getting around 20 minutes with or without GPUs. And you had to fill this big table and prove everything. On SP1, because you actually only prove the execution of the cycles you use, you can be a lot more efficient. And on an empty block, you can get down to 2 minutes. For us, a full one might still take 6 minutes. On the next slide, you'll see that actually real blocks take only about 2 minutes. So we have a little bit of work to get our prover up to the very most performant one that we can compete with. This is from ETHProof, so these are real blocks that a version of an SP1 prover proved. 2 minutes is about accurate, even if it's not empty. And if you get GPUs, it's going to go down even more. But this is not my work, so I don't want to talk about this. Just noting that now we're all working towards the same goal. We have this idea of real-time proving coming. So if we get to 12 seconds, that's really, really huge. We can use that as well. Everyone can now build on a couple key prover technologies, and everyone can win. Some challenges, some of the API needed to be changed. The trusted setup from SP1, we have no reason to doubt, but we might do another one ourselves just so we know we're the honest actor in it. We didn't participate. If you did, then that's good. And although we do love the ability to say that everyone can optimize, it was nice owning our own stuff because we could make direct changes, and now we'll have to talk to other people and make sure that everyone's on the same page. No CCC I talked about. I'm out of time, so I'm going to skip this slide. Future direction, more zkVMs. Hopefully SP1 never has a bug, but if they do, we want to be able to use a different zkVM. We're going to optimize it, regardless of whether that's their prover or our prover. We want to do that. And we also want to consider things like REST. That's it. I'm out of time, so I'll stop there. Do I have time for questions? Or no?
Thank you.
No? OK. Thanks.
I think we have time for one short question. Anyone? I know this is a lot of zk, which is not that easy on the brain. But yeah.
If nobody wants to ask a question, I have some questions. Maybe the one I'm most curious about, how do you think about the security of the prover that you're using? For example, how important for you is the audits, the formal verification of SP1, because these are your users, and so now you're kind of outsourcing. So how do you think about
this? Is by far the most scary part of going down this route. Is before I was fully accountable for my circuits. It was mine, and if I broke them, I knew who to blame. Now I have to try to convince someone else that they've actually got a bug if I think there is one. Obviously, if I have one that I can replicate, it's very easy to do that. But this is very, very concerning from the point of view of like, what if there's something subtle and no one's got it? And so we will take some ownership of our own version of it, and we will talk to people maintaining the code to make sure that it's getting all the treatment it deserves. But I think the easiest remedy for now is to say, have a backup zkVM in case it goes wrong and prove that that is effective. The reality is I'm open to suggestions for doing better. We can get the code audited ourselves too. We can do formal verification of that for everyone. But I think that should be a community effort, and I don't think we're going to be the only one using SP1. So if you're using SP1, you want to improve the security of it, come talk to me too. I'm happy to try to figure out how that looks. Or tell me that I shouldn't be using it, and then I will change it out as quickly as I can. But it has been worked, so we're taking a very pragmatic approach.
All right. Thank you very much.